Hello everyone and welcome to the tutorial. So here we are going to take a look at how to prepare a benchmark using the driver API from MGPU Sim. So if you go to this particular link here in our repository, so there is MGPU Sim, which is where the MGPU Sim code is stored. If you go to doc and then prepare benchmarks.md, that's where this information that I'll be going through in this tutorial will be stored. So you can always refer back to that if you have any questions. If you have any concerns, you can always open an issue or communicate with us. So to get started with here, we need to first look at the code as to how we write a program using the driver API. So for this purpose, it's recommended that you have some sort of ID as it makes it easier to develop the code. So here I'm using the popular tool, which is Golan. So Golan is again IDE tool which is developed by JetBrains, and they provide an easy way to write Go code. So you can do things like click throughs and use them. It's not necessary to use Golan. You can also use other IDEs or any of your favorite IDEs. But I found personally that Golan is pretty beneficial. Anyway, so this is where we will try to explain how we write a main program for the benchmark. So recall that right now we do not really simulate the runtime. So we have our own APIs which are defined in the driver API. And so we need to write sort of what you call the main program or the host program in Go to be able to use a kernel. So for this particular tutorial, we'll just take a look at using the ReLU benchmark, which is a common DNN workload. So this code is present inside benchmarks. So if you go here, ReLU, and then main.go. So this is where the kernel is actually defined, or the main code for the host program is actually defined. The kernels.cl file that you see here has the actual OpenCL kernel. So we can open it here. So as you can see, it's a pretty straightforward kernel and uses 3 different arguments: count, float in, and float out. Now coming back to this, recall that we had defined that in our driver tutorial that you need to ensure that the order of kernel arguments is the same here in the host program as it will be in the main program. So similarly here, we have the kernel arg struct. So that contains these arguments: count. Again, we need to pad this because we mentioned that padding is important. Then we have the input, which is defined as a driver.gpu ptr, and the output, which is again defined as a driver.gpu ptr. So these are the 2 parameters here, and then this is the count. So that's the kernel argument. Now we define another structure, which is a benchmark struct. So that contains all the necessary things that the benchmark needs. For example, access to the driver API, the GPUs, the Hsl binary, which is actually what's loaded after compilation, and then the benchmark parameters like input data, output data, G input data, which is the input data for the device, G output data, which is the output data for the device, and then the length, which is a property for this benchmark, and then use unified memory, which is a parameter that decides whether we want to run the benchmark using unified memory or not. Now, the next function is a new benchmark. So this is where the benchmark is actually created. The context for this benchmark is initialized by using the driver, and then we load the Hsl binary. So the Hsl binary is actually what will be loaded by this particular function, which is the asset, and then we set the Hsl binary to this parameter. So load program for memory would actually load this particular kernel and then store it in this Hsl file, so which is a parameter of this type. The select GPUs is basically used to select which GPUs to be used for running this workload. Set unified memory would basically just use unified memory if it's used or passed as a parameter by the command line. And then finally, each benchmark has a run option. So that's where the select GPU function is called, the memory is initialized, and then the program is executed. Now the initmem function is where you actually initialize all your data structures. For example, here we have 2 important data structures, which is the input data and the output data. These are data structures that will be passed to the kernel. So here we just, depending on whether you want to use unified memory or non-unified memory, so that's why the if condition is there, we call the corresponding driver API, that is either allocate memory or allocate unified memory. And then we use the context that we define for this particular application. And then what is the size. For example, here the size is b.length, which is the length of the workload. In this case, the ReLU workload has a parameter called length, and into 4, corresponding to 4 bytes. And then since it's a multi-GPU application, so the driver.distribute API would be called. So this API is responsible for distributing the data across the multiple GPUs. Then we need to initialize the data on the host. So that's where the input data and output data is initialized. And then we populate this input data field. After that, we need to copy the data from the host to the GPU. So that's why the memcopy h2d API is called. And finally, we come to the exec function, which is where the benchmark would be actually executed. So first, similar to OpenCL command queues, we initialize the command queues here. Then we go over all the GPUs. For example, if there are 4 GPUs, this particular loop will go over all the 4 GPUs. It will select the GPU one by one, that is 1, 2, 3, 4. It will create the corresponding command queue, and then it will create the kernel arguments. So these are the kernel arguments that will be passed to the benchmark. Once the kernel argument is created, which you can see has the same order that is defined in the kernel arg struct, we call the enqueue launch kernel. So this is the similar to how you launch a kernel on a GPU. So there's a similar API in the driver called the enqueue launch kernel. So that takes the queue as a parameter, the Hsl binary, which is the kernel that will actually execute on the GPU, as well as the parameters like grid size and thread block size. Once it's done, we drain the command queue, and once this operation is complete, then we copy the data from the device back to the host. So that's where the memcopy d2h API that is defined by our driver is used. And finally, for correctness, we have this verify function, which is recommended for all the benchmarks. So what it does is that it basically calculates the CPU side data and then compares it to your GPU side data. And if there's any mismatch, then it will report an error. So this is quite important for verification, because without this, what will happen is that we'll have no idea of how to verify our data as if our implementation is correct or not. It's not the benchmark implementation necessarily, but it's also the simulation implementation as to whether there's some bug in the simulator that would have an error. So now this is how the main program is created. This is where the kernel present. And now we need to see how we can use this program to run a simulation. So for that, recall in our previous tutorial, we went to the samples directory here. So we go to the ReLU workload. We have a main.go function. So what this particular package does is it basically initializes the benchmark. So for this particular workload, we have only one parameter, which is the num data. So by default, the value is 4096. And then we have we initialize the runner, which is responsible for creating the simulation engine, building the GPUs, and configuring the GPU builder. Then we call this particular benchmark, which is a new benchmark function that is defined in the ReLU package. We set the parameter of length based on what is passed by the user. So this is something that is passed through the command line by the user. Then we add this benchmark to this particular runner, and we run the workload. So this is which will finally execute the main application and will run the simulation. So that is the thing that's actually compiled when you do go build. It will compile this, and then it will run the particular workload on the GPU simulator. So now that we have gone through this, I just like to do a walkthrough of how you can go through this compilation process. Or there might be users who are interested in looking at the disassembly or on commands on how to generate Hsl binary by themselves. So for that, let me switch my terminals first. So here I'm on an AMD system. So this is a AMD R9 Nano GPU, which has the ROCm ROCm environment installed. So that is something that is necessary for if you want to compile your own kernels. It's not necessary for the simulator to run. The simulator can run even on your Windows PC or Mac PC without any GPU at all, anything related to AMD. But if you want to compile a kernel on your own, like say you want to try out a new benchmark and you need to compile a kernel, then you need the ROCm environment installed, because the compiler comes along with that. So for this purpose, we'll just take a look again at the ReLU workload that we went through. So there are a few commands that are of importance here. All of these commands are listed in the prepare benchmarks.md in our docs. So the first command is how to generate an Hsl binary. So it's simple. We just use the Clang OCL compiler. We pass this flag, which GFX803, which corresponds to our GPU, the architecture we're compiling for. The kernels.cl file is the kernel that we are compiling here. And then the binary is kernels.hssco. So that's the binary that will be eventually loaded and executed. Now, if we want to just do a disassembly, like look at the assembly code, we can again use Clang OCL. So that generates the kernels.disassembler file. So you can take a look here. And there you go. So that's the assembly code for this particular kernel. So you might be interested in looking this, for example, if you have your own workload and you want to see what are the instructions there, or maybe you want to write a micro benchmark in assembly. So you can just use this as a reference. So this particular command will ensure that you get the assembly output. The similar thing can be done also in another way. So if you use the LLVM command here, which is LLVM obj dump, and then use a disassemble flag with this particular MCP option for this particular kernel binary, it will dump this main assembly to standard output. So you can see the what are the commands that are, or the instructions that are present for this particular workload. So doing this way will ensure that, say you encountered an instruction that is not implemented. So you can just look at the assembly and see how that instruction is represented. And from there, you can go to the GCN3 ISA manual and look at how to implement the instruction. Or if you have any unimplemented instructions, we are always ready to help. Now, once you're done with this, again, we can run this workload similar to how we ran the FIR workload in the previous tutorial. So we go to samples, ReLU, we run go build, and then we run ReLU-timing -verify. So again, the workload ran, it passed the pipeline, and the kernel was executed. So again, similar mechanisms on how you do it. So these are some commands that are not something that you will be using regularly if you just want to use the simulator with the workloads that we have provided, but it's something helpful to know if you want to write your own benchmark, or you have an existing benchmark that you need to run with our simulator. So these are the steps you would go through. You'd write the main program in Go, which is like the host program, do similar steps. Almost, if you look at the main programs from all the benchmarks, you'll see that they have a very similar structure, like initializing memory, initializing the GPUs, and then loading the kernel binary in the HSO format. And then it's the similar steps. The few steps might differ depending on how many input arrays you have. The kernel arguments would of course differ because those are dependent on the benchmark kernel itself that you are using. But you can use those currently existing benchmarks as a template for your own implementation. So that makes it straightforward. And then using this Clang OCL tool, provided you have a ROCm machine, which you need anyway to compile the kernel that you want to run. So you need that to generate the binary. And then to study the assembly code, you can just use these tools that are available with Clang OCL and use them to understand what are the different instructions that are not implemented or implemented. So that's it for this tutorial. I'll look forward to the next section.